Okay, so you can see my screen, right?
Yes, sir.
Yes, sir. Okay, great. Okay, I'll switch to conversation mode. Okay, so I will complete or try to complete this introductory motivation behind this course today. So today we will talk about representation issues. So I will start once again with the definition of computation given some language L, which is a subset of some universal set U, and some X in U. Decide whether X is in L or not. So this is the way we formalize computation. And we have seen a couple of examples illustrating that this formalization, or this formalism, is not all that bad. And in fact, it stood the test of time over decades, and it's universally accepted as a good definition of computation. Okay, so today I will talk about the representation issues so that I can make this, I would say, notion little bit more concrete. Okay. So here you see that I am giving two things. First, one language, which is possibly an infinite set, and an element of the universal set to a machine for checking whether X is in L or not, for checking membership of X in L. So first, I will look at the simpler thing, elements of U. Then I will talk about language. In fact, throughout the rest of this course, we will see several representation techniques. So it's not that important to know it fully today. So let us first take elements of U. First, I will make the practical assumption that each element is or has a finite representation. Okay. So I cannot simply feed an infinite description to a machine. Okay, the machine will take forever to read that infinite description. So X must have a finite representation. Later we will see L will also be demanded to have a finite representation, but that's a more complicated issue. Each element of U, the universal set, like X, must have a finite representation. Okay. For example, natural numbers, graphs, and think of other things, maybe strings. Okay, so these all have finite representations. I will formally define string today. And I would not say natural number. The set has a natural, finite representation. These are all infinite sets actually. But each element has a finite representation. Maybe very big, but still finite. Okay. You may actually go to something more like the set of rational numbers, even the set of algebraic numbers, is each such element has a finite representation. But if I go to the set of real numbers, I really hit trouble. Okay. So if I talk about decimal or binary or octal or hexadecimal representation of certain numbers, they never stop. One example is pi. It's an infinite sequence. 3.141592.
So can you please explain what do you mean by finite representation? Each element.
Yeah, this is the example, pi. If I want to represent numbers, real numbers, in, let's say, the decimal representation, then pi do not have one. Pi does not have one, right? It's an infinite expression. This will keep on going. And not only that, because this is irrational, this is completely, I would say, non-periodic. So you cannot find any pattern here, which you can feed to the machine. So if my representation is by decimal expansions, then pi cannot be represented because it's an infinite representation. Okay. But if I use this symbol pi, then this description fits in a finite amount of space. This much space, you can see pi. With all connotations, with all implications, whatever pi means, things like pi, e, you can see these are finite representations. But how many, I would say, real numbers can you represent this way? Okay, you will eventually run out of the, I would say, English alphabet, the Greek alphabet, the Hebrew alphabet, and so on. Okay. In any case, so representing all elements of R is not possible. Okay. What we often do, we make a finite precision approximation of real numbers. And this gives us something like floating point numbers, float, double, long double, and things like that. These are the things which we can do in a finite amount of space. But all elements of R cannot be represented using a finite amount of space. Okay. In any case, if we restrict to, say, natural numbers, integers, graphs, strings, things like that, we can have every element represented in a finite amount of space. Okay. So this is the first thing we will start with. Every x in U has a finite representation. Without that, we cannot feed an infinite presentation like this to the machine. The machine will keep on reading it forever without doing any computation at all. Okay, so that's not a valid suggestion. Okay.
Sir.
Yeah.
Sir, by representation we mean some unique identification for that element, right?
Some way of representing. If I cannot represent it as well, this representation is infinite, and if I cannot represent pi that way, so I introduce a new symbol. Okay.
Means some way or the other we can get to know that this is representing this particular element. So that is
yes. I am representing this thing, whichever that pi is. I am using this e, but you will eventually run out of symbols this way. Okay, so you cannot represent too many things in a finite space. Okay, so this is one thing. Second thing is that this finite thing is important. I would say that every representation, some such finite representation, or maybe I would just say finite, can be encoded as a string over some alphabet. Okay. So for example, if I look at n, the alphabet is something like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, by concatenating these symbols, as long as we want, we can represent each natural number. Okay. And if I look at Z, I may possibly introduce additionally some plus and minus signs. And then usual 0 to 9 should be there. Okay. Q can be elements of Q rational numbers can be represented by adding a new symbol slash something like that. Okay. Or they can be represented as a pair. This is basically nothing but let us say Z cross N. Okay. So if this has a finite representation as a string, this has a finite representation as a string, then I just use some separator, which may be slash. Okay. So the elements of Q can be represented using this set, plus, minus, and add a separator, then usual 0 through 9.
So shouldn't we use n minus 0?
No. Division by 0 is a crime. Don't do that.
Sorry, I didn't get it.
No. This is the denominator. This is the numerator. Denominator is always positive. Do not divide by 0.
Yes, sir. That's what I'm saying. Shouldn't we write n minus 0? N minus element 0.
My definition of n is this. If I imply 0 to be in the set, I will just write n0. Okay. Actually, this is a matter of convention. Some people write this as n, some people write this as n. So,
Sir, just on the left hand side, you have included 0.
On the left hand side above Z, you have included 0.
Yeah. Where?
Above Z, sir. Oh, yes, sir. There.
N. Yeah. You should represent 30, for example. 405. You need that 0, right?
Okay, sir.
Okay, it is the alphabet.
Yeah, this is the alphabet. This is not the set. Yes.
Okay, sir.
Okay. So that's about numbers. If I now talk about graphs, they are actually mathematically two sets, but I can also represent them as pictures like this. Maybe something like this. Okay. So they do not look like strings, right? But the point is that if I give some numbering to them like 0, 1, 2, 3, I have a representation like this. Maybe I start with 4, telling that there are 4 vertices. Then I will use some separator, maybe hash. Then I will say 0, 1 is an edge, followed by hash 0, 2 is an edge, hash 1, 2, 1, 3, hash 2, 3, and then you have to terminate this. So if there is an end of string marker, or you can simply say hash, hash. Okay. So this string, which is again now this string is over the alphabet. You have to use 0, 1 through 9 for representing these numbers. And then you are using two separators, hash and comma. Okay, it's a string over this. Another way is you just write 4 followed by 0 1s, which is basically, I would say, row major representation of the what is that called, adjacency matrix. Okay, if I make this representation, now my, I would say, alphabet becomes 0 1 up to 9 for this part, and 0 1 here, and union hash. Okay, so every conceivable thing can be represented as a string.
Sir, how are you representing this graph by this hash?
Hash is a separator.
What, sir?
Separator. Okay. 0, 1 is, look, here it's 4. It may be 400. So this may be 199. So I need a separator to figure out when this number ends and the next new thing starts. Is it not? Or if you're not comfortable with this, you go ahead with this. So you know adjacency matrix, right?
Yes, sir.
So I can have a row major representation of that matrix. So start with the number of vertices and then use a separator. Okay, and then it's a string of zeros and ones. If there are n here, if there is n here, then if there are n vertices, then this is a string of length n square. Okay. Whatever it is, I can have a string representation.
Okay, sir.
Okay, I can have a string representation of a graph. Okay. So the idea is that every conceivable object, everything maybe, has a representation as a string. Okay. Over some suitable alphabet. So if we make some such encoding scheme for our language, what happens is that we can now, so with this understanding, we take sigma to be an alphabet. Which is by definition a finite set of symbols. Okay, let me introduce some notions about alphabet. Sigma power n is the set of all strings of length n. Okay, so this is, I am just introducing some symbols, nothing to understand really here. There are all strings, of course, over sigma of length n. And okay, then what is sigma power 0?
Empty string.
The empty string. So this is nothing but set this. So I will use this epsilon throughout this course to denote the empty string. Okay. And sigma star will denote the union of all sigma power n greater than equal to 0. The strings of all possible lengths. Okay, these are just some notations. And given that if I can choose an appropriate alphabet, I can anyway represent any finite object. So now one, I would say, question regarding representation is solved. Our universal set U will no longer be set of all integers, set of all graphs. I can, without loss of any generality, take it as sigma star for some appropriate sigma. Happy or not?
Yes, sir.
Okay. There is no harm in doing so. So we will always take the universal set to be sigma star for a suitably chosen sigma, the alphabet. Okay. So this is our first, I would say, simplification. So we will no longer consider languages of numbers, languages of graphs, languages of strings, languages of other I would say things. Instead, we will always consider languages to be subset of sigma star. So languages are subsets of sigma star. Okay. So throughout this course, we will always consider languages which are subsets of suitable sigma star. Okay. So this is how I define languages. Any subset of sigma star. Okay.
Sir.
Yeah.
Means taking sigma star as U is our assumption, or means it is fine for all the cases that we can take sigma star as U.
Yeah, it's because if you have some encoding in your mind, whatever object you get, that can be represented by a string. So there is no loss of generality. It's just a simplification. I would say simplification in the definition. Otherwise, we have to talk about languages of numbers, languages of graphs, and so on. But now I define languages as subsets of sigma star.
So, sir, like whatever language we need to represent the universal set, that language we take as sigma star. Means representation, whatever set of alphabet.
You have some encoding scheme. If you talk about graphs, fine. You fix an encoding scheme. Represent every graph as strings. Consider those strings. And of course, you may talk about what about those strings that do not stand for a valid encoding. So you make some convention that it stands for the empty graph. Okay.
Yes, sir.
Okay. So considering languages as subsets of sigma star is not at all harmful, but it's a very good and simplifying convention. Okay. Not a bad idea, actually. Another thing I just want to say in passing is that you can see lots of symbols here, 0, 1 through 9 hash. Each such symbol has an ASCII encoding, right? Something like an 8-bit binary encoding, right? For example, 0, as far as I remember, it's 48, 1 is 49, 9 is 57, hash has something, okay. So if I think of some such fixed length binary encoding of symbols, then such a string can always be represented as a binary string. Agree or not?
Sir, can you please repeat it?
Okay. Okay. 0. This is ASCII value 48. 1 has ASCII value 49, and so on. Okay. So if I say that I can represent my string over the so-called ASCII alphabet, then for every symbol, I can replace the 8-bit ASCII value. Yes or not?
Yes, sir.
Okay. But then, with the interpretation in mind that I am considering an 8-bit encoding, so I will take 8 bits from the input, one at a time. Then, this is nothing but a sequence of zeros and ones.
Sir, we need a separator as well.
No, that is also a symbol. Hash has some ASCII value, right?
Sir, I mean, we need to find where the binary of 2 will end and binary of a hash will start.
Hash is a symbol. It has an ASCII encoding. Okay. I do not remember. I can check it. Anyway, don't worry about it.
Sir,
Maybe it is.
I mean to say, sir, that if we represent all the characters into ASCII code, then we need to have some identifier from where a computer can identify. So this is the number and this is the character.
No, this hash as a character is there, right?
Okay. Yes, sir. Understood.
Okay, understood.
Yes, sir.
Sir, since we are representing in 8-bit, the computer will take 8 bits like that.
Yeah, something like that. It is not a very important thing. Only thing is that what I want to convey is that in general, if I take the input alphabet as 0, 1, this also suffices without any loss of generality. Okay, hash may have something like 36. So whenever you get that 36, in fact, how is this string stored in something like char star, char array? It's nothing but a sequence of zeros and ones. No.
Yes, sir.
Okay. So this is the important thing. So always, I would say, taking sigma equal to 0, 1 suffices. Okay, but we will not always do it. Sometimes we will take A, B, C, 0, 1, 2, 3, 0, 1, and even we will also consider unary alphabets. Okay. Anyway, so
Sir?
Yeah, tell.
Sir, if we need to represent the universal set of all graphs, then if we take this alphabet, then there will be a lot of strings which do not mean anything at all. So
That's what I told. If there is a string which does not correspond to a valid encoding, okay, you take some convention. Maybe that is just the empty graph.
So having multiple encodings for a single element won't be a problem, right?
Oh, that's not usually a problem.
Okay.
Okay, so maybe since you mentioned invalid encoding, means some object, some empty object, some fixed object. You map all these invalid encodings to some fixed object, like empty graph, empty, yeah, whatever. Okay, that's usually not an issue. Okay. Okay. Fine. So Henceforth, I will therefore pick some sigma, which can be 0,1, but it can be other things also. And we now have the, I would say, liability to represent I would say subsets of sigma star, the languages. This issue I will come little later if time permits today, but anyway, this is the question for the rest of the entire course. So you don't need to worry too much about representation of languages now. What I wanted to say, maybe I would say the algebra of strings. Okay, let me introduce some notions. Okay, so operation on strings. Strings are not exactly, I would say, like numbers. They may be interpreted as numbers, but in general, strings are not numbers. But they support a kind of non-arithmetic operation called concatenation. Okay, which means the concatenation of two strings x and y is nothing but write all the symbols of x followed by write all the symbols of y. Okay. Okay, so all symbols of x followed by all symbols of y. So that is the concatenation of x, y. This is also a finite thing. X and y are finite, strings. And therefore their concatenation is also a finite thing. So this operation is not exactly a good, I would say, arithmetic operation. It is associative, no problem, but not commutative. Does it have an identity?
Yes.
But
Empty string.
the empty string acts as the identity. So identity is epsilon. Inverse, no. You concatenate two strings and get epsilon, so that's not a good thing. This is not what is supported by concatenation. So concatenation is an associative operator with an identity. And if we have an operation which satisfies only this and this is called a monoid. It is not a group, just called a monoid. Anyway, whatever it is called, concatenation is an associative binary operation with an identity. And sigma star is monoid under this operation. Okay. Anyway, don't need to worry too much about this. And then we can also talk about things like prefix, suffix, powers of strings, because they can be defined using concatenation. So X is called a prefix of Y if Y is XZ for some Z in sigma star. No problem, right? So X appears somewhere at the beginning of the string Y, so we call it a prefix. Likewise, I can define suffix if Y is equal to ZX for some. So this part is suffix, this part is suffix. These are just some definitions. Okay. Powers are important and interesting. So given a string x, I define x power 0 to be the empty string. And then for n greater than equal to 1, I define x power n as the concatenation of x with x power n minus 1. Okay, so I'll give you some examples. What is 0, 1 whole power 3? Tell.
Sir, 0 1 0 1 0 1.
Exactly. 0, 1, 0, 1, 0, 1. What is 0 power 3, 1 power 3?
Sir, 0 0 0 1 1 1.
0, 0, 0, 1, 1, 1. Okay, so powers are nothing but an n-fold concatenation of the string with itself. Okay, so these symbols we will use extensively throughout this course. Okay. Fairly straightforward and intuitive, but whenever we raise string to a power, we do not imply some arithmetic operation, but it's basically n-fold concatenation of x. And x power 0, never forget this to be epsilon. Okay. Okay. So these are things you need to know. Just a little bit setting up the notation. Now, I may also talk about operation on languages. Now, they are nothing but sets. The union, intersection, complement, all these things. And some more things like symmetric difference. These are all applicable to languages. Okay. All the things that you can do with sets, you can also do with languages. So all set operations are allowed on languages. But then, since languages are composed of strings which support some kind of, I would say, operation called concatenation, I can also define concatenation of languages. Okay, so if L1 is a language, L2 is a language, I define this to be set of all x1, x2, concatenation of all strings of the form x1, x2, such that x1 is coming from L1 and x2 is coming from L2. Okay. And then I define the powers of a language, L power 0, to be consisting of only epsilon. And for n greater than equal to 1, I am defining this as the concatenation of L with L power n minus 1 or L power n minus 1 with L, whatever. It's the same thing by associativity. So let's take an example. So let's take L to be A and AB. So the alphabet is, let's say, A comma B. What is L power 0? it is always by definition epsilon. L power 1 is nothing but concatenation L with L power 0. Sorry, yeah, L with L power 0. But if I would say append or prepend epsilon here, it remains the same as L. That is A, AB. What is L square? This is the concatenation of A, AB, A, AB. And what are the strings? AA, AAB, ABA, and ABAB.
Also A and AB, right?
Huh?
A and AB also concatenation with an empty string. Because empty string is also a part
A,
of that.
AA.
Only A. Is empty string a part, an element of the language?
May or may not be. For example, this L does not contain the empty string.
Okay.
Okay.
Like we'll implicitly specify that.
Yeah, this is a finite thing, right? The finite language consisting only of two strings,
okay,
A and AB. But never forget that by definition, L power 0 always contains epsilon, irrespective of whether epsilon is there in L or not. This is by definition. Okay.
Yes.
Okay, so this is by definition.
Sir,
Yeah, tell.
sir, for all this discussion, by strings we mean a finite combination of the alphabets, symbols from the alphabets, right? So each element of sigma star is itself a string.
Yes. So string is a finite. Okay, I should have defined this ordered sequence of symbols. Okay, finite, and it's an ordered sequence. So AB and BA are not the same strings. Okay. So finite is important, ordering is also important. Okay. Okay. Fine. Okay, so that is fine. So with this notation, I have just another concept. The star of a language is the union of L power n for all n greater than equal to 0. This is called the asterisk of L or cleanest star. Okay. So this is just setting up some notions and some notations. We will throughout this course use these notations. Okay. Okay. Now there is a question. Maybe I will just very briefly address this issue. So given L and X, decide this part is now understood. Next question is how to represent languages. If L is finite, then I can simply say it consists of string 1, string 2, string 3, and string n. N may be huge, each of these strings may be huge, but this is still a finite representation, as I have done here. We have two strings. One is A, other one is AB. Okay, so I can represent this explicitly, exhaustively this way. Okay, but that is a bit too restrictive. If L is an infinite set, then what to do? First of all, I am going to feed the description of L to a machine. Okay. So one important thing is that any description of L must be finite. Okay, we cannot represent infinite languages by explicit enumeration of these strings because that description is infinite. Therefore, we have to do something with infinite languages. Okay. So now let us see that although we have several infinite sets, we can still have, let's say, finite representations. The set of all primes. I can represent it this way, right? Let me write this set of all n in n such that n is greater than 1 and for all u v in n equal to uv implies u equal to 1 or v equal to 1. This is a compact definition. We know that this set of primes is infinite, right? There are infinitely many primes. Okay. Or maybe I write it this way. Or v equal to 1 or v equal to 1. Okay. So this is a precise finite way of writing the set of all primes. And we know that primes are not finitely many in number. There are infinitely many primes. But still, you see that with all our conventions, connotations, we still have this finite description of the set, this infinite set P. Here, first of all, I have used this set building notation. I am using, for example, set membership notation epsilon A belongs to. I am using logical constructs like this and or for all. Okay, implies. Also, I am talking about arithmetic operations like multiplication. Okay. So this is a finite representation with a lot of meanings associated with every symbol appearing in this representation. That's not a problem anyway. Okay. Also, when we represent numbers, there is also some kind of interpretation, like whether it's a decimal interpretation or binary interpretation, whatever. But any such representation will always have some interpretation. But you can see that the set of primes can be defined in terms of logical and arithmetic operations using symbols this way. So this is a finite representation of the set of all primes. Okay. Happy or not?
So we can do this for some infinite languages, but not all of them, right?
Yes. Maybe I am running out of time, so maybe next day, tomorrow, I will spend some 15-20 minutes for completing this issue. Yeah, what it really means in computer science. Okay, but you see that this description is full of connotations and logical things, arithmetic things. Possibly this is not a very suitable thing that you can feed to a machine. Okay. Because too much interpretation is hidden behind this. Okay. They are not, I would say, essentially or very machine worthy. Okay. So still I want some other ways which are more machine worthy. So a dumb machine can simply read that description of L and figure out what it stands for. Okay. So the next question that is more machine worthy representations. Okay. So there are several ways of doing it. Maybe I just mention one possibility is you define classes of machines, which we will do. And second, what we will do is recursive definition using what is called grammars. Okay, so these two types of representation of L is all this course deals with. We will do it. Okay. We'll build classes of machines. They represent languages, even infinite ones. We will also represent languages using grammars, which is a kind of recursive ways of building strings in the language from a set of primitives and rules, a set of rules. Okay, so that you need not worry about, because throughout this course, you will see more and more sophisticated ways of representing languages. What is important today is that it can be done, certain infinite languages can be represented in a machine-worthy form, or even in this form. Okay. What does that mean? So that implication I will just mention before starting the proper course. Okay. Okay, I think we should stop because it's past 1 p.m. Okay, so if you have any immediate queries, let me know.
Sir, language is finite means its cardinality is finite, right? Of that set.
No.
Like, what is a finite language and infinite language? Like, both of them are sets.
Okay. Finite means the number of strings in that language is finite. Infinite language means number of strings in that language is infinite.
Means the number of elements in L should be a finite number for L to be finite, right?
Yes. That's how I define finite languages.
Okay, sir.
But whether we are dealing with finite languages or infinite languages, our description of L must be finite. That's a different thing. Finite languages do not pose any problem in a finite representation, because every element of that language is a string, which is a finite thing, and there are finitely many such strings, so we'll just write them one after another. No problem. The only problem comes when you want to represent infinite languages in a finite amount of space. And that can be done this way, for example, or using grammars or by types of machines.
Okay, sir.
Sir, like if there is a finite language, but we can always concatenate the strings for infinity.
I didn't really understand this question.
Sir, let's say we have a finite languages and there are n members. So we can concatenate those n members for infinity so that we can get an infinite length of string.
That's possible. For example, look at this. So L1 will contain A, L2 or L square will contain AA, L3 will contain AAA, and so on. So if I look at the asterisk of this L, it will be an infinite language. Among other things, it consists of all A power n things. Yeah. So
sir, how a language can be finite?
No, L itself is a finite language, right? Its asterisk is infinite.
Okay, yes, okay, thank you.
Sir, can a finite language be of size n? I mean, size of LF0.
Size of?
LF0. Like the size of natural number.
I will come to that. And in fact, it is only for this reason we have studied this LF0 and countability and uncountability issues. So I could not cover it today. Tomorrow I will do.
So could you please give how we can describe the set of natural numbers in, like how we describe primes? We use the set of natural numbers for the definition of primes. Say how we define the natural numbers in this way.
Natural numbers are nothing. Oh, I see. If you want me to define natural numbers, then you are. This is a very difficult thing. So let us take this holistic notion that these are the whole numbers, positive whole numbers, 1, 2, 3. And
then we are going to the whole numbers and
no, the question is that there is a description of all these things, but that is too much of mathematics. Okay. I think let us not, I will not say I know a great deal of these things, but yeah. So why is 1 plus 1 2? These are questions will be in the scope of this course. Okay. In fact, as I was looking at a documentary film yesterday, so Hilbert spent something like 100, 200 pages to prove that 1 plus 1 is equal to 2. Let us not worry about these issues. This will lead us nowhere for the moment, for this course at least. Okay.
Can you upload this scribe?
I can. I can. But there is not much here. Anyway, this is still not, I would say, a proper entrance into the course. I'm just setting up notations. But anyway, this can be done. There is nothing, I would say, wrong with uploading this material. Okay, so any other immediate questions? So I will address some issues about finite representation tomorrow. Then we will go to finite automata. Okay, if not, let us stop. Bye.
Thank you, sir.
Thank you.
Thank you, sir.
See you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.